context switch is implemented in most every OS. Right? This is a stack pointer. How is it used during context switch? This data member. Then maybe 2 minutes, just everyone think about it, and then we'll ask you. Now you can discuss among yourself, right? Ask around if you are not sure. This is the single most important question that if you want to make sure that you understand how context switch works, this is the single question that you can understand. Okay. All right. So yeah. So let's try to answer this question and yeah. Please go ahead.
So you say it's to keep track of where the program was in execution. So when we do a process switch, we write it down into the stack, as well as all the other execution and registers. So when we go back to continue the process, continue the execution, we know where in the stack where and where the execution of the program were. So we can reinstate all the registers.
That's very good. That's very good. All right. So the context of the execution, right? So let's use this diagram to illustrate what we mean at high level. We have three processes, right? Three processes, 1, 2, 3. And suppose during process 1's execution, its stack keeps growing, and the stack pointer points to here. Right? And what we mean by the stack pointer points to here, it means that the stack pointer register, right, during the execution of process 1, the stack pointer register is incremented automatically every time you push some item onto the stack. Right? This is to say, okay, the stack pointer register is incrementing automatically until it reaches this point. Right? And at this point, suppose a context switch happens. Okay, the context switch happens. what you want to remember, right, we want to switch from process 1, let's say, to process 2. Okay. When we do this switch, what you want to remember is the location of this stack pointer. So that in the future, when we, let's say, switch back to process 1, we know where is a context, right? What is a stack? Where should we continue execution? Okay, and so this stack defines the context of the problem execution. Right? So we want to remember where this stack pointer is when we switch back to process 1. And that is why when we do this context switch from process 1 to process 2, we're going to store the register value of stack pointer. Right? Remember here, the stack pointer is in the register, SP register. We're going to store the value of this SP in this SP register to the corresponding process entries data member. And it's a process stack pointer data member here, somewhere here. In process 1's process table entry. Okay? Because if you don't store it, it's going to be overwritten, right? This SP is in its value is in the register. When you switch to process 2, it's going to use this register. Right? So you have to store it somewhere. So you store it in process table, its corresponding entry, process 1's table entry. So that in the future, when we switch back to process 1, we can load this SP. We load this SP1 back into the SP register. Okay. And now that's how you restore the execution context of process 1. One tricky thing is this stack pointer only remembers the status of the stack. Right? It remembers where is the bottom of the stack. Why? But why do you not need to remember the location of the execution in the program of process 1? Or more specifically, problem counter. Right? When you execute the program, in each process, when you execute the program, every time when you execute one more instruction, the problem counter increments. And the problem counter is the one, the register that you use to remember the location of the execution in your program. When you switch back to process 1, you want to go back to that program location and continue execution from there. Right? That is also part of your execution context. Where is that stored? Program counter. Right? Think that here we are only storing this stack pointer in process table entry. Right? Problem counter is also important. Otherwise, you don't know where to return to in the your problem execution. Yes.
Is it stored in the stack then?
In the stack, right? Remember, the large part of the context switch code is pushing items onto the stack before you switch to process 2. Problem counter should be one of the register whose value is pushed onto the stack. Right, so when you return, you need to pop out the problem counter. Okay? All right. So that is right. That is almost the single most important question that you need to understand about context switch. Right? The stack pointer, how it's stored and how it's stored to memory and restored when the context switch happens again. Right? And in almost every OS, its implementation is very similar. Okay, but now let's look at the details. Right. Yeah. So we already explained this part of the code, but let's quickly go through it again. Right. So when reset is invoked, we explained that reset is typically invoked when the timer interrupt is triggered. Right. So if the time slice allocated for one process is used up and the timer interrupt is triggered, it's going to call this reset. And the reset will eventually call this context switch with two parameters. One is the old process, it's stack pointer. It's old process meaning the process that need to be swept, need to be switched out. The new process stack pointer. This new process means that the process needs to be switched in. Okay, we call context switch with these two parameters, and what the goal is try to achieve is to store the current stack pointer to the old processes table entries this specific data member, and use this new process's stack pointer to load it into the stack pointer register. And that finishes the context switch. Right. So now you see that why I asked the previous question. Right. You see context switch, you only use it two parameters. Understanding how these two parameters are used is critical for you to understand what context switch really does. Okay. All right. Now, about context switch, right? Let's go through context switch again, and I think we were here at line 27, right? And we almost finished explaining this code, but let's go through them again. And I would assume that most people might already know the first part of the code, so I'll go through it quickly. Right? When context switch happens, right, when it's invoked by the reset function, the function invocation will first push these parameters onto the stack. Right, these new process stack pointers address. This is the old process stack pointers address. Okay, remember it's their address in the BSS section. So it's not the value of the old stack pointer and new stack pointer. It's their address in BSS section. Okay, and it also pushes the return value, the return address.
Can you clarify when you first threw it in push? Is that a context switch or then
It's in reset. Here, right? When reset calls context switch, whenever you invoke a function, the first thing that is performed when you invoke a function is push the parameters onto the stack and also push the return address onto the stack. Right? These are the two parameters pushed onto the stack. The return address, right, which is the line that should be right after this invocation, should be this line return. Right? They are pushed onto the stack. Right? So these three things happen when the function is invoked. This happens when you enter context switch. When context switch starts execution, you see that this EBP is pushed onto stack by line 11. And this is when context switch really starts execution. Okay. All right. So the first thing it does is to push EBP onto the stack, and this EBP is the reset EBP. It's not a context switch EBP. Right? Remember, EBP is the stack base register. Okay, it points to the top of the stack for the current function. Okay, so now I will explain that right now. Right, so at line 12, we move ESP to EBP. What does this mean? We explained it in the previous lecture. Right? We move ESP to EBP. What does this mean? What is the implication of this line?
Where the stack currently is now the base.
Exactly, right? So remember, as ESP increments whenever we put some item onto the stack. So ESP, let's say, when it's functions context switch invoked, it starts from here. When we push item, the parameters onto the stack, ESP is incremented here, and it's incremented again, and incremented again. And this is when we finish the execution of line 11, this is where ESP points to. This location, right? This is where ESP points to. The bottom of the stack points to here. When we move ESP to EBP at this location, it means that we're going to use the EBP register to remember this is the stack base for context switch function. This is the starting point of the stack for the current context switch function. What's the point of doing this? Why do I want to remember the starting point of the current function stack? Right? Stack base remembers the starting point of the current function. It's stack. Why do we want that? Later it's used, right? In this specifically in this context switch function, later this EBP is used. The reason is that if you remember this the top of the stack for the current function, we can use this EBP to easily retrieve the parameters. Later, this new SP and old SP they are used, right? Later in the execution of a context switch. And how to get them? Right? We use the EBP which points to this location, and add a few, so move up a few items, right, a few bytes, to retrieve old SP and new SP. That's what stack base pointer is used for. It remembers the base of the current functions stack and use that to provide quick access to the function parameters. Okay? All right, so that's why we are doing line 12, right? So we, at this point, we move ESP to EBP. This is to remember, right? So where is the stack base for the current context switch function? And then after that, we push all the flags, we push all the general purpose registers, and the ESP, right, grows with these items pushed onto the stack. Okay. And after this point, after line 14, that's where the magic is going to happen. And we explain this. Okay, so line 18. Let's carefully go through this again, right? Because this is where the magic happens. Line 18, we explain it. What does it do? Actually, let's put these two things together, right? So, line 18 and line 20, these two lines, 18 and 20, what does it do? Yes?
It's saving off the old stack pointer.
Saving off the old stack pointer, right? And then maybe can you break it down, right? These two lines, what does each of them do?
So the APDP kind of goes to that memory, the old SP memory location, and it puts that into register.
exactly, right? Let's go through it slowly. I think in case there are people who are not very familiar with this assembly language, parenthesis means that you're using the value as an address, as a pointer, right? So without a parenthesis, you are directly using this register with and its value, right? So if it's on the left side, you're using this value. If it's on the right side, it's a target, right? You are sending something to the target. If it has parentheses, you are using it as a pointer. Okay, so that's the semantic of this assembly language. Here in line 18, we're using EBP as a pointer. And we move this pointer up by 8 bytes. Okay, where does EBP point to? Remember, EBP is a stack base of the current function, so EBP points to this place, right? So this is where the top of the stack is for context switch function. Okay, so EBP points to here, and we move this pointer up by 8 bytes, so it points to here. Okay, and we are going to put this address, right, so the content, into this EAX register. So now EAX is value is the same as this one. The address of the old process is stack pointer in the process table in BSS section. Okay, and the next step is that I'm going to use this EAX as a pointer, which means that here I'm going to store the current value of the ESP, which is here. ESP right now points to here. I'm going to store the current value of ESP to the address pointed to by EAX. And the address, the memory location pointed to by EAX is this address, this memory location. Okay. So this finishes, remember this memory location is a data member in the process entry of the old process. So we store this ESP's value in the old process's process entry, the stack pointer data member. Okay. Does it make sense? So this is the first step. Right? Yes.
This line 20 compile because I'm in like x86 64 when I'm trying to do that, it doesn't work until it's like a global variable which is like pulled into a line. For these would that line work? No.
Yeah, you run it, it works. Right. This is how Dino is written. Right. You compile it, it runs. Okay. Okay. So that is line 18 and 20. Okay. Now line 21 and line 27. Right. These two lines are doing similar things, but the previous two lines, 18 and 20, is storing the current stack pointer to the old process's process table entries stack pointer data member. These two lines, 21, 27, is doing the opposite. Right? It's loading the new process's stack pointer from the memory to the register, to ESP register. Okay, so this is why we do this. We first again use the EBP plus 12 bytes, which EBP plus 12 bytes is here, right? And you put this value into EAX, right, which means that the EAX contains this pointer now. Okay, and you use this EAX, you get its content, right, which is the new process's stack pointer stored in the processing tree, and you put it, you move it to ESP. This finishes the loading of the new process's stack pointer from memory to register, to ESP register. Okay, when this line finishes execution, the context switch finishes. Oh, not completely finishes. You need to pop some registers, but this is where the magic finishes. Right? The context switch already happened. Because once this line 27 is executed, now where is ESP pointed to? This question is simple. So where is ESP pointed to after this line 27 finishes execution? Previously, ESP was pointing to here. The bottom of the old process's stack. After line 27 finishes the execution, where is ESP pointing to?
Where the new stack stop.
The bottom of the new process stack, right? Suppose this one, and we put it here because we are just showing that, suppose this is the stack of the new process, right? After line 27, ESP will point to here. This is where the context switch already happened. When the ESP points here, you are already in the new process context. That's after line 27. Okay? Now the magic happened. You want to, what's the next step? You want to clean up the items that you pushed onto the stack. Right? So that's why after line 27, now you are in a new process context. You're gonna pop the items, right? At line 31, you're gonna pop these general purpose registers, right? And at line 32, you pick up EBP before restoring, right? So you're gonna restore this EBP, right? So 30, this is yeah. So ESP after pop up all the general purpose registers, ESP points to this place, and you use at line 32, you use the ESP plus 4, which means that it points to here, and move its value to EBP. Right? That's how you restore the EBP. Okay. Right. This is restoring the EBP for the parent function, which is remember this EBP is the stack base for the rescat function. Here it stores the stack pointer, stack base for the rescat function. Okay, so after this step, EBP is restored, and then we pop the flags. Right, so we pop these flags, and the stack pointer move to here, and then let me see. Yeah. Yeah, and then at this place we skip EBP because we already restored EBP. Okay, and then call return. When we call return, it's going to pop this return address, and this return address, when it's popped using this return instruction, it will be saved to the program counter register. Okay. So the program counter will be overwritten using this return address. So you resume execution of the rescan function. Right? And it will also pop out these parameters. Here, there's some subtlety here. Okay, why do we want to pick up the EBP before restoring the interrupts and then skip the EBP later, right? So this feels weird, but there's a specific reason why we need to do this. We'll explain this later, right? Forget about this subtlety. First, try to understand the overall picture, right? So what is performed after the context switch magic happens? It's straightforward. Right? We pop all the general purpose registers, we pop the flags and EBP, and we use this return address to return to where? This address. Okay? When RET is this instruction is executed, it returns to this location because this is a return address that is remembered, that is pushed onto the stack when context switch is invoked. Right? Remember, when context switch is invoked, it pushes this parameter, and this return address onto a stack. These three things are pushed in this order. And right, so that's why when we call return at this location, it uses this return address, and this return address is the last instruction in the rescan function. And the new process will continue execution from there. Okay. All right. Is that clear? Does it make sense? This is the process of a context switch. If you understand it, this is maybe one of the most important topics in OS. How is context switch really implemented? Right? And if you understand it, it's you will understand the core of time sharing operating system. Right? How to switch context from one process to the other. Okay. All right. So these, if that's okay, then we'll try to explain this subtlety, right? So here, why do we pick up EBP before pop these flags and then skip the EBP later, right? Why don't we just pop general purpose registers, then pop flags, then pop EBP, right? Just pop them one by one. Why don't we do that? Anyone knows? I don't expect that anyone to know it, right? Because it's related to process creation, which we haven't taught yet. We haven't discussed. It's specifically related to process creation. And why we have to do this? So if you ignore process creation, actually you can do this. If you can just pop general purpose registers and then flags and then EBP and return, you can just do this. You don't need to do this weird thing that you pop EBP first and then flags and then skip EBP later. Okay. Yeah, I don't expect anyone to know, right? So the reason is that the flags, right? So when you pop these flags contains one special flag, which is whether the interrupt is enabled or disabled. Right? So whether interrupt is enabled or disabled. And that flag could be overwritten. Sorry. There are two possible values of this flag when you execute this pop flag. In almost every execution, this flag, the interrupt flag, will be disabled. In almost every case, except for one special case, which is if the process is just created. Okay. In almost every other case, the interrupt is disabled. So if we ignore process creation, it's safe to just pop the flags with interrupt disabled. And because if an interrupt is disabled, you won't have another process that switch in because of timer interrupt during this execution. But the special case is that when process is created, its interrupt flag is actually enabled. So if somehow you are switching in the process, this flag here is interrupt enabled. And if you pop these flags, it will override your interrupt flag and make it enabled. And if a hardware interrupt or a timer interrupt happens at this point in time, right after you pop these flags and enable the interrupt, and happens at this place, then it would crash. It would cause confusion of execution. The EBP is not popped, and later the execution. Sorry, let me think. When suppose at this point the interrupt is enabled and the context switch happens again, right? This process of context switch, right, will be confused. So the context switch is not designed to handle this specific scenario where an interrupt could happen at this specific location. Okay. Yeah. So the detail of this is more obvious when we explain after we explain how process creation is performed. Right? And we'll go to there first and finish explaining context process creation, and then this will become more obvious. But this is a subtlety that is not that critical, because this is specific to x86, some architecture. Right? This is specific to x86. If you look at the ARM hardware architecture, the implementation of a context switch using ARM assembly, you will see that there's no such problem in ARM. And this is because this is a problem for x86 architecture. So it's not a general problem. It's not the most important concept. Okay. All right. So yeah. So this is how the process creation is implemented and how the stack changes during process creation. But we'll come here later. We'll explain at a high level how process creation works, and we'll come back to how the stack changes. Yes. Can you speak louder? I couldn't hear you. Sorry, I can't hear you.
Where does the new SP and old SP second set of data come from? Are those the arguments of the context switch solutions? Or
Where is this new SP and old SP coming from? Is that the question?
yeah,
The second one. This one?
yeah.
Yeah. These are pushed onto the stack. Right? These are pushed onto the stack when the new processor, the new process was switched out before. Right? Which means that the new process, normally the new process was switched out because a rescat was invoked when the new process was current process on the CPU. Right? So when that new process was switched out before, rescat was invoked, and these were pushed onto the stack at that point in time. All right, and that's a good question. Okay. All right, now let's let me see. think this slide I haven't uploaded to the ED discussion, but I'll upload it immediately after this lecture. Right. Process creation. Okay. We will cover process creation today, and process termination, and the process suspension, and the resume. We'll talk about them later. Okay. So there are two possible scenarios when we switch a new process, when we perform context switch to switch in a new process. One possibility is that the new process was switched out before using rescan. The other possibility was is that the new process was just created. It has never been executed before. Right? The new process was just created. And when after we created a new process, we want to switch. We will switch it in to put it onto the CPU to continue execution. And we want to do that using the same API, with the same functionality, which is a context switch function. And this makes it tricky. Right? This new process, it was just created. It has never been switched out before. So its stack is empty, right? Remember that when we switch in the new process, we expect its stack to look like the structure we just showed. Right? It has the parameters of a new process, old process. It has the return address of the rescan function, and it has the general purpose registers and EBP and so on. That's the expectation of the new process's stack when we switch the new process in, right? But when we do that for a process that's just created, this process does not have anything on its stack. If we use context switch to switch in a new process, and it has nothing on its stack, the context switch code does not work. Does it make sense? Right. So that's why when we create a new process, we are doing two things. One is that okay, we need to allocate the data structure for this process. We need to initialize its process entry and so on, the data structures. Second, we need to push things onto its stack to create a fixed stack, just as if that this new process that was just created, just fake that it has been switched out before. Right? Although this newly created process has never been executed by the CPU, it has never been switched out, we want to fake its stack so that it looks like it has been swept out before. Right? Does that make sense? Just two things. When we create a new process, we do two things. One is that we initialize all its data structures. Second is that we initialize its stack and make its stack look like this process has been switched out before. Okay? That's a goal we want to reach when we create a process. And if you understand that these are the high-level goals and how it's implemented, then you understand how process creation works in Zeno. Okay? Right, so these are the things that are performed during the process creation. You allocate a stack for the process being created. Right? Every process needs a stack. You need to do this allocation. And you fill in the process table entry. The process table entry is a data structure for a process. It remembers the information about the process. So you need to initialize it. Right? And then you fill in the process stack to have a valid frame. Okay? this is where we fake, right? A valid stream means that we are faking that this new process has been switched out before. And this is where the subtlety happens. So we need to make sure that the stack frame of the newly created process looks like it has been switched out before. Okay? Right. Allocation, initialization, fake the stack. These are three things. Okay? Right. Yeah. To design decisions, choose an initial state for the process, choose an action for the case where we'll look at this in more detail later. Okay. Yeah, I don't think we are. Yeah, we don't need to understand this in detail, but the only thing we need to understand is this one, right? So this init RET, right? This init RET is defined to be function user return, right? So this function, okay. This is the return address that is pushed onto the stack when the process is created. It's different from the return address of the context switch, and later we'll see when this init RET is used. Okay. Right. So this is where we explain. Okay, we need to create a pseudocall on the initial stack. The trick is we want to arrange the stack as if the new process was stopped in a call to context switch. This means that it was switched out before. Okay. These details we'll look at them later after we examine the code of process creation. Okay. Right. The steps for process creation. Right. It allocates a process table entry, allocates a stack, and then place values on the stack as if the top function was called. There is a pseudo call, and arrange the stack so that the context switch can switch back to this process. Okay. The implementation details depend on the hardware, and we will look at the example code for the x86 processor, right? We focus on this. All right. So this is the code of process creation in x86. This part is very straightforward. We allocate some local variables, so that is helpful for the this function execution. Right? Later we'll explain what they are, but for now you don't need to remember them. Okay. And these parts we will explain them later. Right? So this is get stack is allocation of the stack. Right? So this API is able to allocate a stack for the current the process you want to create. And how the allocation works is related to memory management, which is a later topic. Okay. For now, you just need to know that after this point, we have allocated a stack for this process. And then what happens here is we are initializing the process table entry for this process. Right? We get the process table entries pointer for this process that we are creating, and then we initialize its stack state. We initialize its priority. We initialize its stack pointer, and so on. So this part of the code initializes the process table entry for the process we are creating. Okay. this part of code initializes the device this process uses. It's not the most important thing, right? Okay. Right. Now here, starting from this point, here, starting from this point, we are doing stack manipulation. We are going to initialize a stack for this new process. This is where it becomes interesting. And we are going to look at so this, starting from this until the end of this process creation function, right? This is where things get interesting. And we will look at this piece of code in the other slide. We will look at this piece of code in this slide because right, so on the right hand side you can see how the stack looks like when this part of the code executes. Okay, and you can see how we figure. It looks like how we make this stack look like a process that was just switched out. Okay, right. Starting from this point. Right, you have a stack magic, put the stack magic on top of the stack for this process. It's not the most important thing, right? It's just a value, special value you use to check where the top of the stack for a process. Okay, and right, so the stack pointer, right? So yeah, so yeah, you have a variable that is used to store the, it's called an SAVST, which means that save the stack pointer, right? So it's going to save the stack pointer. And this SADDR, stack address, right? This is the pointer that we are using, right? This is the stack pointer. SADDR right now points to this place, this location, and it's going to be incremented every time we push something onto the stack. Okay? So you can see that here, whenever we push an argument, right? So here argument n until n argument 1. So this is in this loop, right? Number of arguments, we are pushing the arguments that we use to run this process onto the stack. And it happens like this. Every time we push an argument onto the stack, we're going to change this SADDR, which is a pointer we use to point to as a stack pointer. Right? This SADDR is essentially the stack pointer. Okay. Right. So we haven't started using the ESP register yet. Right now we're just using this SADDR as a stack pointer to initialize this stack. Okay. So in this loop, we push all the arguments onto the stack, and then after that we push this init return onto the stack. Okay. This is when the process finishes its execution, it's going to return to this address, and remember this address is points to a special function that terminates the current running process. Right? Init ret. Okay. Sorry. Let's. Just to make it clear, okay, that init ret, that special constant or macro, it points to the address of this user ret, this function. So putting this address onto the stack, it means that when the process finishes execution, the last function it executes will be this function. When they return to this function, it will call kill, which terminates the current process. Okay? Right? This init RET points to that function which kills the current process. Right? So that's why it's put here. So which means that this is the top of the stack for this process. If we finish this execution of this process, we're going to execute this function and kill the current process. Okay? Next, the next thing is this function address. What is this function address? You want to take a guess? Nice. Give it a guess. What is this function address? So this is where it gets slightly different compared to context switch. Yes?
I was going to say stack point.
Function address? That's not the stack point, yes?
It's the processor's name. What the drag is.
That's getting very close, right? It is related to when how the process is created. When the process is created, it has a few parameters. One of the parameter is the process name. What is the other parameter?
Program
The
counter.
address and address. And text file.
Sorry?
The text in the text file where the code is written for.
Where the code is written, or the function, the starting function of this process, right? When you create a process, you also tell this process what is the function that you want to run inside this process. Okay? This function address is points to the function that you want to run in this process. Okay? What is this? So here, remember in the context switch, the stack, right? So in this stack, right? In this stack, what is the equivalent in terms of position, right? The function address, when the process is created, is pushed onto the stack in the same location as which item, right? Which of the item in this stack has the same position? Yes. Return address. Exactly, right? Return address. Function address and return address, they are take the same position. They are equivalent, but their meaning is, what does it mean? So remember this return address. What does it mean? It means that when the context switch finishes, when you switch back to this process, what is the line that you're going to execute? Right? What is the line that we're going to execute here? The return statement of the rescat function. Right? The return address here is the return statement in the rescat function. We're going to continue execution from there. Right? This is when the context switch happens for a normal process. What happens? But for a newly created process, because rescat was never invoked for the newly created process, right? What do you want, right? When context switch happens for this newly created process, what do you want it to return to? You want it to return to, or more precisely, you want the process to start executing the function you give it in its parameter. Okay? That is why here you put the function address at this location. What you are expecting is that after we finish, after we set up a stack, in the future, a context switch will be invoked to switch in this newly created process. It's going to pop up these registers one by one, blah, 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 and similarly as what you observed in the context switch execution we explained before. And after the context switch finishes, all of these things will be popped out, and it will pop out this function address using the RET instruction. And once it pops out this function address using the RET instruction, the process will continue its execution from this function address. Right? And this function address is the function that you pass to the process in its parameter, and that's where the process starts execution. Okay? Right. So this is the key, right? So we put the function address here. So when this context switch happens for this new process, it's going to return to the to this function and to this user program and start execution from there. Okay. All right. So all right. So next. That's a high level idea, right? How we fix the stack for a newly created process. This is a key. A function address is a key. Okay, and after that it's similar, right? So this is the address of the stack magic entry. This one. So this is remember in the previous in the previous context switch stack, what is this location stored? The EBP of the rescat function, right? The base stack pointer of the rescat function. Right? Here we are just storing the base stack pointer of the entire process. Right? Address of this entry, it means that this EBP points to the top of the stack for this entire process. Okay, and flags and general purpose registers, they are pushed onto the stack the same way as how they are pushed onto the stack during context switch. Right? In context switch, you push the flag, you push the general purpose registers. When the process is created, you do similar things. There is a slight difference, there's some subtle difference, which we'll explain later. But at a high level, we are trying to do the same thing, right? We push the fixed stack base onto the stack. We push the flags. We push the general purpose registers. This is what we are doing here. Return address, fake EBP, flags, and the general purpose registers. After this is done, this stack looks like a process stack that was switched out, who has been switched out before. Okay, what does it mean? It means that if we execute the second half of the context switch function, right? Which means that from line 31 to 36, if we execute this line 31 to 36 using this newly created process stack, it will succeed. And it will, after executing that part of the code, it will start execution from the function address of the user program that you give to this process. Okay? All right. let's imagine. I think the remaining time, let's imagine. We have 2 minutes. Let's imagine how the context switch happens. Right. After this process is created, the stack is initialized like this. It's suspended first, and then it's resumed. So which means that forget about these things, but it's put in the ready state and added into the ready list. Okay, so the newly created process is added into the ready list, and in the future, when the timer interrupt is triggered, and when the reset function is invoked, if this newly created process has a high priority, it will be picked as a new process to switch in. When that happens, when it's picked as a new process to switch in, when that happens, how does the context switch function execute? When the context switch function executes second half, how does the stack change? Right, let's go through this quickly. Right, this is a new process that is picked. When context switch function executes, what happens to this stack? Right, anyone want to try to explain it at high level? Right, yes?
Does it fall into
Exactly. Exactly. Right? So remember, in a context switch function, this part of the code that's poking things out of the stack, this is executed on the for the stack of the new processes that's getting switched in. Right? This is the part of the code that's executed on the stack of the new process. Which means that when context switch happens for this newly created process, when it's switching this newly created process inside to the CPU, it's doing the same thing. It's going to pop all the general purpose registers one by one, and then it's going to pop the flags, and then it's going to pop the EBP, and then it's going to use return, right? Pop the return address and start execution from there. Okay? And when it starts execution from there, from that function address, that's the user program that you give to this process. Right? That's when this process really starts execution. Okay? All right. So that's at a high level how we create a new process and arrange its stack as if it has been switched out before. So that when we use a context switch to switch in this new process, it can work correctly. Right. There are some details like registers. We have some special, some subtlety here, how we store these things. But those are the details. We will explain it later. For now, I just hope everyone can understand the high level.